Chapter 2, Section 3. This is now where we are going to take the first and second derivative tests and apply it to curve sketching. And this is curve sketching that's going to be more specific than what we have already done. All right, so if we think about the first derivative test, if we have f prime that is changing from positive to negative, then that's where there is a local maximum at that value. And what this means is that we can infer that f of x then increases, then it decreases. And this is what that would look like. And then if the first derivative was negative to positive, then there's a local minimum because the original function decreases and then it increases. And then the final thing is if there is no change of the sign, whether it's either positive on both sides or it's negative on both sides, then there is not a local extremum, and it would look something like that. All right, so the second derivative test refers to the second derivative. So we know that if it's less than 0, then this is concave down, and if the second derivative is greater than 0, the original is concave up. Then this is a new part C here says if the first derivative at the value a equals 0 and the second derivative equals 0, then it has a shelf. And that is the picture that I just drew above, where it would increase and then kind of have a shelf right here. Anytime we are looking for an inflection point, that's when we're going to set f double prime, the second derivative, equal to 0 and then solve. So this is actually what we're going to do. So instead of just assuming this is where it exists, we're actually going to find the exact point. Okay, so when we've sketched before, this should convey the general shape of the graph. It needs to show where the original is defined, where it's increasing and decreasing and concave up and down. Now, something to note, though, is that there are no inflection points plotted. You're not going to see them plotted. We are going to actually go back, solve for them, and do that ourselves, but you're never going to see those as points needed to connect your curve. All right, so remember that a tangent line drawn to a relative max or min of a point has a slope of 0. This is huge. So let's go back and draw that. So that would look like this at all of these extremums. All right, and then if we have a in the domain such that the first derivative is equal to 0, this is what we call a critical number or a critical value of the function. But then if we take that critical value and find the y, this is what we're going to call a critical point. So what this is saying is we have critical values anywhere the first derivative equals 0. So everywhere I just drew a tangent line, those are the critical values or critical points depending how you group them together. So a critical point is going to be your x comma y, and a critical value is just the x value. So if you look at the graph above, we have a critical point at -3, 2, -1, -3, 2, 1, and 4, -1. So then you go back and you just list all those x values, and those are the critical values for x in terms of x. Okay, so again, like I said, inflection points are not identified on the curve above, but we're going to mark them on the graph and estimate them. So if I go back up to the graph, then I can estimate that there's a critical value around -2, -1/2, 1/2, -1, and then 3, 0. Okay, so I'm going to list them here. So -2, -1/2, 1/2, -1, and 3, 0. So they're not needed to be plotted, but we can still find them on a graph. All right, so that note down there says these are the roots of the first derivative. So because my critical points represent the min or the max of the original, we know that those become the roots of my first derivative. So let's graph a little sketch just on a number line of the first derivative. So -3, -2, -1, 0, 1, 2, 3, 4. So I'm just going to label my critical values here. And then this is where I would plot a point because these are the roots. And then because the inflection points is where we have now, I guess, a min or max of our first derivative, we know that if this was -2, 1/2 down here, we're going to go and curve like this. And then around 1/2, we're going to curve up and come back down. And then at 3, the same thing. This is a rough sketch. Okay, so this is the first derivative of that graph we have above. Now, we haven't really seen one like this before, but this one is actually a quintic function. It has 5, a degree of 5. So now we go down 1, and now we have a quartic function for our first derivative. So just something to note as well. Okay, so all that stuff that we just talked about is going to be important, but we're going to get even more specific. But before I want to do that, I want to kind of review what a sign chart is. Some of you may have done these, I think, in honors pre-calc. If you did regular, you would not have, but it's a concept that maybe you did in Algebra 2 with quadratics, possibly. So if not, just follow along. It's not too bad. But given this function right here, and I actually want to add to the notes and do this too if you don't have this on your copy, I want this to be the first derivative because that's truly what we care about. So if the first derivative is that quadratic where we can clearly see our roots at -4 and 1, then I'm going to draw a sign chart, okay? Now, it's important to note that this is a number line. Okay, so we have roots at -4 and 1. Now, I put them in that order, not because they were listed in that order, but because it's a number line. -4 is to the left of 1. So, how do we know, basically, if our parabola is going to open up or open down? That's the ultimate question. So, we know it's going to go through at -4 and 1, but in what way? So, what we're going to do is we're actually going to test points. Okay, so let's test -5 because we need to test a point on each side of the critical points. And again, these -4 and 1 are critical points because on the chart before we were talking about the fact that where the tangent line equals 0, those are your critical values. So if I'm telling you this is the first derivative, then the roots are the critical values. So if we test -5, when I plug in -5 to that function, -5 plus 4, -5 minus 1, I get a negative times a negative, so I'm going to get a positive. And again, this is a sign chart, so that's all I care about. Then if I test 0 is always the easiest one, and that falls in the middle, then I get a negative because I get 4 times -1. And then let's just test 2. I'm also going to get a positive times a positive, which gives me a positive. So this implies right here, this is how I would fill out my sign chart. And then I know now that the original function is increasing, decreasing, increasing, because this is the first derivative. So if I wanted to sketch this first derivative graph, then I know that we have -4 and we have 1. My roots are here, and then it's going to go like this. Again, I'm not too focused on where it crosses yet. Eventually we will, but this is just the basic concept of a sign chart. Alright, so the first 2 pages of notes are just kind of to bring all this together, but these next examples are how it's going to look. And then you'll actually see examples 1, 2, and 3. I'm going to walk you through how to do this. And example 4, there's no guided notes at all. So you're kind of have to just start getting to know this process. All right, so we have the cubic function listed below, and we're going to try to find the local min and maxims of this point, and ultimately our point is to sketch them, or sketch the graph, the original. So the first rule, or first step, is to take the first derivative and set it equal to 0 and then factor it. So using the power rule, I did this. This is my first derivative, and now I'm going to factor and solve. And when I do that, again, the roots are the critical values. The roots of the first derivative are the critical values. So that's what I'm looking for. So those are my factors, and I can finish by saying x equals 3 and 1. And now I just found my critical values, 3 and 1. But now I need to find the critical point. So all I'm missing is the y value. So what we're going to do is because these values are the roots of the first derivative, but they are also the x value of your max and your min of the original. So since I'm looking for the max and min, I'm going to take these values for x and plug it into the original f of x to find the corresponding y. Okay, so even though we just worked with the first derivative, we're really trying to find the critical points of the original function f of x. So basically, I'm going to do f of 1 and f of 3. So I just plug them in for x with using my calculator, and I get 2.3 if I rounded it, and I get 1. So my critical points are 1, 2.3. And 3, 1. All right, so now we want to identify the inflection point and find that y2. So remember, that's going to involve the second derivative. So there's two kind of thought processes you can use. I'm a little bit more in favor of using the second derivative and solving, but I'm going to first just say the inflection point is between the two critical values, 1 and 3. So therefore, we can say it's 2. And then we can go from there. Personally, if it doesn't work out nice and easy like this, I would rather solve and have that kind of just be my go-to each time. So I'm going to say, but I know that the inflection point exists when the second derivative equals 0. So first I need to find the second derivative. So I'm going to look up top at my first and do the power rule again. So 2x minus 4. And then I'm going to set that equal to 0 and solve. And when I solve, I get x equals 2. All right, now I need to find the y. Well, if this is the root of the second derivative, which is the inflection point of the original. So therefore, I'm going to take 2 and I'm going to plug it in to the original one more time, f of x. Because they share that value of 2 for x, I can do that. So even though I just was working with the second derivative, I'm going to take 2 and I'm going to find f of 2. Because we want the inflection point that exists on the original function. So when I plug all that in my calculators, please watch parentheses with fractions, I get 5/3. So my inflection point is 2, 5/3. Okay, so now this is kind of where we can do our sketching. And again, we're not going to use the calculator to do this. So I set it up in kind of three ways. So, all right, so I have my first one. I'm going to do 3 number lines. Now this first one up at the top is always going to be just a rough sketch of f of x. It's just going to show you the shape and where there's a min and max, but not the exact point. We're going to do that after we finish this whole thing. So this is just a rough sketch. All right, so we're kind of getting at 15 minutes, so I'm actually going to stop the video and make another one. So now move on to video number 2 to continue.